Okay, good evening. Welcome to the second half of geometry lecture on section 2.4 of Geometry Revisited. We're going to continue learning a little bit about fun properties of altitudes, the orthocenter, and circles involving the triangles and altitudes. So yesterday, let me draw the picture here. I've got a triangle ABC. I've got altitudes CF and BE, so those are right angles there. And yesterday we learned that B times H, BH times HE equals CH times HF. That was a very clever proof, and that is actually a pretty remarkable fact. Now what we're going to do is continue down and show a couple of amazing theorems. I'm going to let Z and Y be any points on side AB and AC, and we're going to draw the Chevians BY and CZ. So any point, there's nothing special about them at all. And we're going to, once we draw the point BY, we're going to draw a circle with diameter BY. And once we draw CZ, we're going to draw a circle with diameter CZ. The first thing to notice is that those circles, no matter where you pick that point on the side AY, those circles pass through the feet of the altitudes. And let's see why that's going to be the case. The reason is BE is perpendicular to AC, so that's a right angle. And so when I draw a triangle here, BEY, it turns out that the angle BEY is a right angle. That means it's inscribed in a circle with diameter BY. So therefore, the circle with diameter BY goes through the point E. Similarly, the circle with diameter CZ passes through the point F, which is the foot of the altitude on the other side. That in itself is kind of an interesting point. But here's an even more interesting thing. We have those circles. Circle with diameter BY, and we have the circle with diameter CZ. And we know that inside of that circle, BH times HE, we have a chord, and we know that BH times HE from section 2.1, so Geometry Lecture 10, we know that's equal to the power of the point with respect to the power of the point H with respect to this circle. Similarly, we know that CH times HF is the power of the point H with respect to this circle with diameter CZ. But we know those two things are the same, which means we know that the power of this point H is the same with respect to those two circles. And that tells us that H lies on what we call the radical axis. I can't remember if that's from section 2.2 or 2.3. So the theorem is, if two circles are constructed with Chevians as diameters, any point Y, any point Z, two circles are constructed with Chevians as diameters, the radical axis passes through the orthocenter of the triangle. And remember, their radical axis is just the point where the powers are the same, and it's going to pass through their intersection point. So here's their radical axis, but we know that passes through the orthocenter of the triangle. And we can extend this theorem for any three circles, and I don't want to draw a third circle, and I would pick a random point on this side, say, and draw the circle. For any three non-coaxial circles having Chevians for diameters, H is the radical center of the triangles. And we define radical center in, I think, section 2.3. It's just the point that has the same power with respect to all three circles. So it's actually a fascinating fact. They point out in the book that this second theorem is usually given as an exercise and can be disguised a little bit to say, for example, that the three circles with medians as diameters have a radical center equal to the orthocenter, or the angle bisectors. But it turns out amazingly that it's true for any Chevians. It's actually a pretty remarkable theorem. So now I got two more quick things I want to prove. The first is an extension of the second theorem, which was mind-blowing. And then one quick thing, and then we'll be done. So let me draw the next picture. Okay, here's the next picture, and the next thing we're going to talk about. We're going to get to one of the craziest geometry theorems I've ever seen. So here's the setup. You have a triangle ABC, and we pick points X, Y, and Z, Z being on side AB, Y being on side AC, and X being on side BC extended. So the points can be on the extended sides too. And we just pick these points X, Y, and Z such that they're collinear. So that means I can draw a line through X, Y, and Z. So we just find those 3 points. And then we draw the Chevians. I haven't drawn the Chevians in because it makes the picture very complicated. But I draw the Chevian to BY and draw a circle with BY as diameter. So the diameter of this circle is BY. I draw this big circle here has diameter AX. And the small circle has diameter CZ. Okay. So I hope you can see the picture. I know this one's getting complicated. But here's an amazing observation about the picture, and then I'll tell you what the theorem is. We set this up so that X, Y, and Z were collinear on the sides of AB, AC, and BC. But another way of looking at this picture is instead looking at the points X, B, C, X, B, and C. And those lie on the extended sides of triangle AZY. So X is on ZY, C is on AY, and B is on AZ. Okay? That's another way of looking at it. Another way we could have looked at it is we could have looked at the points Y, CA, and those lie on the possibly extended sides of the triangle ZXB. Okay? So you can see that C, Y, and A lie on the sides of ZXB. And then there's a third triangle, or a third set of points, ZAB, Z, A, and B, right here, Z, A, and B. And those lie, can you see the triangle whose sides those lie on? Those lie on the extended sides of the triangle CXY, so this triangle here. So we actually, there's 4 ways of looking at this picture in 4 triangles. We can look at the triangle ABC. Here's my little pointer. Use this. We can look at the triangle ABC. We can look at the triangle AYZ. We can look at the triangle BZX, or we can look at the triangle CXY. And any way we look at the picture, it's the same thing. We've drawn the other points lie on the extended sides. And then we draw the diameters. We draw in our circles, and it's always the same circles. AX, circle with diameter CZ, and the circle with diameter BY. And what we learned last time is any of those 2 circles have the orthocenter H of the big triangle ABC. Any 2 of those circles have that point lying on their radical axis. But here's the thing, the radical axis of the 4 triangles that we're talking about, ABC, I can hardly see them, AZX, maybe its orthocenter is over here, or maybe it's up here, maybe this orthocenter is down here, and then the big one maybe BZX, the orthocenter is right there. In any case, the 4 orthocenters of those 4 triangles are not the same. So we get this incredible theorem, and actually I forgot to write it down, so let me just read it to you out of the book. We get this incredible theorem. If 4 lines meet at 6 points, A, B, C, X, Y, and Z, so forget the triangles that we talked about. You just draw 4 lines, any 4 lines, and they meet at points A, B, C, X, Y, and Z. So the set of points X, B, C, Y, C, A, Z, A, B, Z, A, B, and A, Y, C, or sorry, and X, Y, Z are collinear. So we have 4 lines meeting in 3 points, and we have those set of collinear points, 4 lines meeting in 6 points, and we have the pairs of triples of collinear points, then the circles AX, BY, and CZ as diameters are coaxial, and they're orthocenters of the 4 triangles AYZ, BZX, CXY, and ABC are collinear. Now, that is an incredible theorem of geometry. So I don't even know what to say. I mean, you would think if you have 4 random lines meeting in 6 random points, you wouldn't be able to say anything about them. But it turns out you just draw a few circles and you look at the triangles and all the orthocenters all line up. I find that absolutely remarkable. Okay, one last thing and we're done with this section. Okay, here's the last fun little property, and this only takes a second to see, and fortunately the picture is much easier. So we have a triangle ABC, and we draw the altitudes AD, CF, and BE, and we extend them to the circumcircle. Just extend them so they intersect the circumcircle at D prime, E prime, and F prime. You'll remember from yesterday that we proved that HD equals DD prime, HE equals EE prime, and HF equals FF prime. Oh, but they're not necessarily equal to each other, so I should label them like that. So H is the orthocenter of triangle ABC by definition, and then we sort of see the surprising fact that A is the orthocenter of triangle HBC, of this triangle. Okay, why is that? Well, what do the altitudes look like? Well, HD is the altitude of triangle HBC, sort of by definition, and we can extend that altitude like that. If we extend side CH over here, we'll see that BF becomes the altitude to side CH. Similarly, if we extend side BH over here, see that CE is the altitude. So where do BF, CE, and HD intersect? They intersect at A. So A is the orthocenter of HBC. Same argument. B is the orthocenter of AHC. And C is the orthocenter of AHB. And that allows us to show a remarkable fact. If we draw the circumcircles of these 3 triangles, BHC, BHA, and AHC. I'll go over here. It turns out that, even though my drawing for AHC didn't work right, it turns out that all 4 of those circles have the same diameter. So all 4 of those circles are congruent. And that's a pretty remarkable fact. And it turns out it's not that difficult to prove. And the way you prove it is by remembering that HD equals DD prime. So I can draw this circle instead. Oop, better not draw it in purple. Let's draw it in orange. I can draw the circle BDC. And we talked yesterday, and you can see it in the picture here. This is a right triangle. The angles are the same. That was what we proved yesterday, that this angle is equal to this angle, and they share a side. And that means that the triangle BD prime C is congruent to the triangle BHC. So the triangle BD prime C is congruent to BHC. And if 2 triangles are congruent, their circumcircles are going to be congruent. But what's the circumcircle of triangle BD prime C? It's the same as the circumcircle for ABC. So that means that the circumcircle of BHC, which is this circle in red, is exactly the same size as the circumcircle of the original triangle. So that actually is a pretty remarkable fact. So to sum it all up, draw the altitudes of a triangle. They intersect at a point H called the orthocenter. Draw the circumcircle of the big triangle, and draw the 3 circumcircles formed by the triangles of that are made by one of the sides and the orthocenter, and all 4 of those circles have the same diameter. Pretty remarkable. This was a very difficult section, section 2.4, but some pretty neat geometry theorems. You're starting to see that this book has an incredible amount of depth. So thanks for watching. Look forward to the next section tomorrow.